In 1637, a French philosopher sat down and wrote one of the most important sentences in the history of thought. He was not thinking about computers. Computers did not exist. He was thinking about the nature of the mind and whether anything, a machine, an animal, another person, could truly be said to think. The sentence he wrote was this: "I think, therefore I am." That philosopher was René Descartes, and the question he was wrestling with, what separates a mind from a mechanism, is the question that, 3 centuries later, gave birth to artificial intelligence. By the end of this video, you will understand why a 17th century mathematician, a 19th century logician, and a Victorian engineer are the true ancestors of every AI system running today.
Plain Machine, AI in plain English.
This series traces the full story, from the first question of whether a machine could ever think, all the way to the systems on your laptop right now. It's a better story than most people realize. Let's get into it.
Let's begin with a problem that sounds deceptively simple. Can you write down the rules of thought? Not the contents of thought, not what you think about. The rules, the structure, the logic that makes an argument valid or invalid, regardless of what the argument is about. For most of human history, the answer was, of course not. Logic lived in the mind. It was an art, not a science. You learned it by reading Aristotle and by practice. It wasn't the kind of thing you could reduce to symbols. Then came Gottfried Wilhelm Leibniz. Leibniz was one of the strangest minds of the 17th century, a philosopher, a mathematician, a diplomat, a theologian, and a man who invented calculus at roughly the same time as Newton, entirely independently. He was relentlessly ambitious, and one of his most ambitious ideas was this: that human reasoning could be encoded, that logic was not a mystical art, but a formal system, that arguments could be checked the way you check arithmetic, by running through the steps. He called this idea a calculus ratiocinator, a calculating system for reasoning, and he went further. He dreamed of a machine that could perform this calculus, not a machine that thinks, but a machine that could evaluate whether an argument was valid or not, a logic engine. He never built it, the technology did not exist, but the idea that thought has structure and structure can be mechanized never quite went away.
Leibniz had the dream. The next piece of the puzzle came 2 centuries later from a self-taught English mathematician named George Boole. Boole was not born into privilege. His father was a shoemaker. He taught himself Latin and Greek as a child, and mathematics largely on his own. By the time he was 20, he was running a school to support his family. By the time he was 30, he had done something no one had managed before. He had translated human logic into algebra. In 1847, Boole published a short work called The Mathematical Analysis of Logic. It made a claim that must have seemed almost absurd at the time, that the rules of logical reasoning, and by extension, the rules of thought, could be expressed entirely using the symbols of mathematics. His system was simple and radical in equal measure. Every logical statement could be reduced to a binary value, true or false, 1 or 0, and those values could be combined using a small set of operations, and, or, not, to evaluate any logical expression, however complex. Think of it like this. In ordinary language, "it is raining and it is cold" is either true or false as a statement. Boole showed that this kind of compound logical statement, connecting simple propositions with and or not, could be evaluated mechanically by anyone who followed the rules of his algebra, without any intuition or judgment required. This is called Boolean algebra, and it is not ancient history. It is the precise mathematical foundation on which every digital circuit in the world is built. Every transistor in your phone is implementing Boolean logic. Every time a computer evaluates an if statement in code, it is doing Boolean algebra. This is not metaphor, it is literal. Boole died at 49, in 1864. He did not know what he had made.
Now let us add the third figure. Because while Leibniz was dreaming and Boole was theorizing, someone else was trying to build. Charles Babbage was a Victorian engineer with an obsession. He wanted to eliminate errors in mathematical tables. These tables, lists of logarithms, trigonometric values, navigation calculations, were computed by hand, by rooms full of human calculators, and they were full of mistakes. Mistakes that cost lives when ships navigated by faulty charts. Babbage designed a machine called the difference engine, a mechanical calculator capable of computing these tables automatically to high precision without human error. He spent years and a significant portion of British government funding trying to build it. He never completed it. The engineering tolerances required were beyond what Victorian manufacturing could reliably achieve. But in the 1830s, Babbage had an even grander idea, the analytical engine. Unlike the difference engine, which could only compute specific tables, the analytical engine was designed to be programmable. It would take instructions on punched cards, borrowed from the jacquard loom used to program patterns in woven fabric, and execute arbitrary calculations in any sequence the programmer chose. It was, in its architecture, a general-purpose computer. Not electronic, it was mechanical, powered by steam. But its logical structure anticipated nearly everything that appeared in the electronic computers of the 1940s: a processing unit, a memory unit, sequential execution of instructions, conditional branching. It was never built in Babbage's lifetime, but it was designed. The blueprints existed.
Here is the gap worth sitting with for a moment. Leibniz in 1674, Boole in 1847, Babbage in the 1830s. None of them talked to each other. Leibniz died before Boole was born. Babbage and Boole were contemporaries who barely acknowledged each other's work. And yet, they were working on the same problem from three different angles. Leibniz, thought has structure. Boole, that structure is algebraic. Babbage, if it is algebraic, it can be mechanized. Each insight depended on the one before it, but nobody in the moment could see the chain. That is how foundational thinking works. The pieces accumulate across generations, and the connection only becomes obvious in retrospect. The field of artificial intelligence did not begin with code. It did not begin with computers. It began with this question: can the logic of the mind be captured in a formal system? And it took 3 centuries and 3 very different minds to get close enough to an answer that building something became possible.
Now, here's what this actually means if you work with AI tools, because this is not just intellectual history. The ideas Leibniz, Boole, and Babbage developed are embedded in every AI system you have ever touched. Understanding them changes how you think about what AI is and where it runs into limits. First, if you have ever wondered why AI is so reliable at certain kinds of tasks and so unreliable at others, Boolean logic is a large part of the answer. AI systems are extraordinarily good at tasks that can be decomposed into formal rules and evaluated against structured data. Classification, pattern matching, logical inference over defined categories, these are tasks where the Boole to transistor chain is operating at full strength. The AI is not thinking, it is executing a very sophisticated version of what Boole described in 1847. Where AI gets less reliable is in tasks that require genuine judgment, weighing values that cannot be formalized, understanding context that was never specified, navigating situations that fall outside the training distribution. That is not a Boolean problem. That is something else entirely, and we will get to what that something else is later in this series. Second, if you are making decisions about which AI tools to use for which tasks in your organization, the Babbage framing is genuinely useful. Babbage's analytical engine was not limited by the quality of its design. It was limited by the maturity of the engineering that surrounded it. The same is true of AI today. Many of the limitations you encounter in enterprise AI tools are not fundamental limitations of the technology. They are engineering and integration constraints, the tolerances that haven't yet been achieved. Understanding the difference between "this is a hard limit of AI" and "this is a current engineering constraint that will eventually be solved" is one of the highest value mental models in this field. Third, there is something genuinely important about the timescales involved here. Leibniz had the vision in 1674. A working computer that could implement it appeared in the 1940s, nearly 3 centuries later. We are now fewer than 80 years past that first working computer, and the systems we have built are already remarkable. The pace of this progress is not slowing. That is worth understanding, not as hype, but as historical context.
So, where does that leave us? We began with Descartes asking whether a machine could think. We've spent this video watching 3 men across 3 centuries take that question apart and rebuild it in a form that could eventually be answered not philosophically, but mechanically. Leibniz gave us the belief that thought has structure. Boole gave us the mathematics to describe that structure. Babbage gave us the architecture to implement it. None of them saw the chain they were building, but the chain was real. In the next video, we arrive at the moment where all of this accumulated thinking finds its sharpest question, the one that finally gave the field its name and its first real framework for progress.
In the next video, we go to 1950, but we arrive knowing something that most people who write about the Turing test never mention. Turing didn't invent the question. He inherited it from centuries of accumulated thinking about what it means for a system to behave logically. And knowing that lineage changes how you read what he did. It was not a leap. It was the next step in a very long chain. That's video 3 in this series, and I think it lands differently once you've seen where the chain starts. Subscribe if you want the full arc. Each video builds directly on the last, but they're designed to work as standalones too if someone else finds this channel first. I've put together a 1-page AI glossary, 30 essential terms, plain English, free, link in the description. It's a useful reference for everything we're building in this series. This is Plain Machine. Thanks for watching.